Okay, time for potential difference homework. Let's see what we got here. Suppose sketch error showing relative force when the work done is positive. Oh, okay. So this is just review, force, and displacement. Negative. So force in the opposite direction of S, and 0 force is at 90 degrees. Okay. Object travels from point A to point B while two constant forces of equal mass are away. Is total work? Okay, it says. Okay, so it's going from point A to point B. So, ooh, that's bad. Let's see if I can do a better job than that. Let's see. Try again. Okay, so F1 is negative. Angle is 180. And the equation is Fs cosine theta phi. Okay, F2 is in the same direction, so it's positive. And in particular, the angle here is 0. And the network is 0 because we have Fs cosine of 180 plus Fs cosine of 0. And if you, let's see, we put this as F1, 2, but we said F1 equals F2. Speed of the object, how can I tell? Well, work total equals delta KE, the work energy theorem. So it's equal. All right. An object travels from A to B while two constant forces are of unequal magnitude. Okay. And it's A to B once again. Oops. Wow, let's see. Okay. All right, so F3 is negative, angle 180. F4 is positive, angle 0. Network is negative because we have, let's see, F4 S cosine of 0 plus F3 S cosine, 180. So F3 is greater than F4. Okay, so it's less than, because once again, W total equals delta KE, and it's less than 0, so it slows down. Okay. State. No. It's speed of the object. Okay, I suppose then, strictly speaking, F net equals 0. And well, let's see. F net equals MA, and F net is less than 0, so acceleration is less than 0. And let me make sure. It's point, and then, because I'm calling this the positive direction. And that doesn't prove it slows down, but A is 180 to S. Okay. Okay, so well, work net, if you like, equals the change in kinetic energy. So positive net speeds up, negative net slows down. Is your answer? Oh, yes, but I don't know. How does one explain this? Blindingly obvious? I don't know. Trying to think. I'll explain. Oh, yeah. Work net is proportional to or goes as F net. Yeah, because work net is equal to F net dotted with S. There you go. Okay. The diagram right shows top view of positively charged rod. Point line of plane near the electric field vectors. Okay. So it's hard to do. I'll just draw them sort of off a little bit. So EZ equals EX, EY equals EW. Particle along a straight line from point W to point X. Oh, well, so SWX, okay, E parallel with S, so that implies the F equals to QE is parallel to S, so positive. It travels from X to W. Well, E is, I don't know, how do you say, anti-parallel. S, so negative. anti-parallel is 180 degrees. So, travels from X to Z. Okay, so the F vector is always going to be parallel to radius vector R constant because it said circular arc. So E vector constant and E vector is perpendicular to S always. Oh, 0. So we're only on number 2, huh? 6 pages. Wow, not even halfway, huh? Oh no. Oh, this is the tutorial. Okay. I was thinking it was the homework somewhere. Okay, compare the work done by the electric field when the compare the work done by the electric field when the particle travels from W to X to that done when the particle goes from W to point Z. Well, we said that work Wx is greater than 0 and work xz equals to 0. This is because the F of the E, if you like, is parallel to S, and FE here is perpendicular to S. W, compare the work done with particle trail. They're equal and opposite. Because the delta R in both cases is equal, and so then the the force is not constant. Let's see. So yeah. Force as a function of R. Oh yeah, and also both on radius vectors and F of R Wx is the same as F of R Zy. It's just the F Wx is 180 from F Zy. Oh, actually, that's not right. Okay, what I want to say is SWX opposite to SZY. 0 as we already said that W work for W x equals the negative work zy, and work xz equals 0. So work total equals work wx minus work wx plus work xc equals 0. All right. Suppose particle travels from W to Y on the arc shown. Okay, once again, constant force and constant 90-degree angle. And so work equals 0. Wi is the work done by the particle. Oh, it's 0. Yeah, because let's see, it's from WXYZ, huh? So let's say A. W to A, to work W, what did I write there? Okay, let's be careful. W from W to A is greater than 0, and W from A to Y is less than 0. Oh, it's the other way around, because we're talking about the work of the field. So I'm pushing against it, and this is greater than 0, and the delta R from W to A equals the delta R from A to Y. And, oh yeah, let's call it theta of F, how do we put it? So for, oh boy, yeah. Oh yeah, so that's good enough. The radius vector, the change in radius is the same. And so that means that, yeah, so 0. All right. So work WA equals the negative of work AY because of this. All right, compare the work then. 3 different paths in part D. From W to point Y. All the same. And equal to 0. Well, duh. Jesus, because all the same. Suppose the charge of the particle in section 2 is increased from plus. The work done. Uh, um, okay, the work. Oops. Okay, so the work of 1.7 will be greater than the work of 1 because F equals QE, and and work equals F S cos theta. So greater F and greater work. How is the quantity work divided by charge? Okay. So let's see. Oh, right. So F equals QE. So work is proportional to Q. So if we work over Q, it's constant. Because we're going to have Q E S cosine of the angle divided by Q. Okay, the electric potential. And this is the work per charge. This unbelievable. Oh, we just wrote this up. Oh boy. Does this quantity, this is dumb that I'm writing this up because I already filled this in. Should just scanned it. Is this going to sign the charge? Oh boy. No, because work is proportional to the sine, and Q, sine of Q, U is proportional to sine of Q. So you'll either have a neg over a neg or a pos over a pos. Okay, 4 points, equidistant. Charged particle mass is released from point W and is later be particle. Let's see. This is, yeah. So, it's positive. Ikes repel. Oh boy. So since I've already calculated all that, I'm gonna hold off and put this in later. Okay.